Welcome. Thank you for coming to the 2023 Geophysics Field Camp community presentations. We'll have a couple more people filtering in because apparently it's easy to get lost in this building. So everyone here knows that we have a Department of Geophysics. I'm not sure everyone here knows that we're actually the oldest Department of Geophysics on the planet. And we're about to turn 100 years old. We were founded in 1926. This is from the American Association of Petroleum Geologists, the bulletin for AAPG. December 1926, we announced that we were born. First class was taught in 1927. And if you go back through the years, field camp and field work has been integral to our department. We've been applied geophysics to the natural environment pretty much since we were founded. If you go back to the October 1950 issue of Mines magazine, which you can find at the library, you can find a flow chart for classwork. I shouldn't use this. I should use this so the people online can see it. You can find the flow chart for classwork. The bottom 4 blocks are undergraduate, the top 2 are graduate, just like we have flow charts in 2023. That's the most recent one on the right, 1950 on the left, and highlighted you'll see in 1950, Mines Geophysics undergraduates needed to take 4 credits of field work their senior year. Fast forward, what, 73 years now? Mines Geophysics seniors, just before they start their senior year, need to take 4 credits of field work. This has been a thing that's been going on in our department for longer than pretty much any place, continuously or not continuously. It's in fact so important to us as a department that we highlight it multiple times for our 100th anniversary, which is coming up in 1926. We want to ensure the legacy of field camp for future generations, so the next 100 years of field camp students or geophysics students get the same experience that you're going to hear about today from our current students. On bottom, you see kind of a little bit of how our field work has evolved over the years. Bottom left, you have Carl Hyland actually with an old seismometer. That exact seismometer is sitting in my lab down in the basement of Green Center. If anyone wants to see it, it is not in working conditions. But, you know, we go from kind of the first ever seismic recording device. We start to drill shot. I think that's a shot hole drill right there. I don't know, Todd probably knows. That's from Todd's era. Third photo, you see us setting off some explosives back in the days when we used explosives at field camp, which went up through the 80s, I believe. I have one role for our field camp now. I should have introduced myself. I'm Matt Siegfried. I'm the field camp director and assistant professor in this department. I have one rule for our current field camp, and that's no guns, no explosives. So we don't use Betsy guns, I don't want shotgun shells, and we don't use explosives, sadly. But you'll get to see what we use instead. And then on the right, we get into the 80s, 90s, up through the 2000s, where we start to get computers in the digital age of geophysics. And our field camp has been keeping up with these technological revolutions in our field since the beginning. Our department head, Paul Salva, can't make it today. But he always talks about, I would have invited him up, and he would talk about what he loves about our field camp is that actually the undergraduates run it. We're just there to kind of give them some bumpers about how to do field work and do field experiments and turn that into science. And so if the undergraduates tell us to do something, we have to do it. So maybe that's burying a vertical magnetometer. This thing's 4 feet long, vertical. So, you know, I had to go out. This is the field camp director digging holes. I also had to level it, which is why I'm down here taking a selfie. If, you know, the undergrads need a geophone pole placed, they call up President Johnson. They're like, we need to get this node deployed right here. And so that's President Johnson. He came out this year to help us out with field camp. We also go out into the community. We went up to Steamboat Springs this year, our 2nd year there. They were having a geothermal public forum, and one of our students, Dawn, who you'll hear from later, raised her hand when the former governor of Colorado, Bill Ritter, was talking, and asked some pretty hard questions. You can tell they're hard because look at these people's faces. Like head on a swivel. Oh my God, who is this person quizzing the governor? These are the students we're training. And it's all because we get to do this amazing adventure, spend 2 weeks up in Steamboat Springs, come back for 2 weeks and process the data. And you'll hear all about that from the undergraduates in a second. It's not just a Mines thing though. We bring other collaborators out with us. Here are some folks from USGS Water who also have a project in Steamboat Springs. And so now our students get to work with USGS scientists. We have Colorado Geological Survey scientists out there. We have scientists from other universities, Oregon State. Who else did we have this year? University of Nevada, Reno. Whole host of folks. We're trying to
industry, both consulting and
lots of representation from industry, which the undergrad will introduce you to just after me. I don't want to spoil things, but this is just, I just want to set the stage for them to start talking about what they've actually been doing for the past 4 weeks and the amazing science that we get out of it. We also get to do this in a beautiful place, which helps with the motivation. And so this was our lunch or our morning view out of our classroom windows for 2 weeks up in Steamboat Springs. And this is also our field site. And so the places we'll talk about are mostly just right in Steamboat Springs proper. If you've ever been up there, you know they have amazing geological features that turns out we don't know that much about. And so I wanted to give the floor to 2 of our undergraduates to give a bit of an introduction to this year's Geophysics Field Camp. And they'll launch us into the 5 presentations we have.
Right. Hello, everyone. I'm James McCall.
And I'm Hussein Al-Farid, and today we will be giving you some insight about our field camp. So first of all, we cannot have a field camp without a field. So this year, and as we did last year, we went to Steamboat Springs. So other than being one of the most beautiful cities in Colorado, it has many unique geological features that we as geophysicists are interested in. So it has springs in its name, and it has many springs in there. So the water system is something that we are interested in. Also, there was some faults that weren't fully mapped and some other unique geological features that we are interested in. So we went there and did some surveys. So there was some work done in the past, but it was like in the late 80s. So there was some master thesis done by a student, which gave us like a broader terms about the geophysical surveys that were done back in the 1979. Also, the USGS showed some interest. We saw some folks this year doing some research around in there. In addition to that, the Colorado Geological Survey did some geothermal mapping in the 1980s. And last year, there was some research done, but that wasn't enough to fully cover Steamboat Springs. So this year, when we went to Steamboat Springs, we were permitted to the red areas in the map. We didn't cover all the areas in there, but we went to almost all of them. We were focusing on some areas more than the other areas, like the Black Silver Springs, and we did many surveys in there. So our goal of field camp is to apply what we learn in the class in the field. So we got the opportunity to do 9 different surveys in and around Steamboat Springs. So we get familiar with the instruments, we learned the science behind them, and we had fun.
Yeah, so getting into the fun here, we're starting with some hammer seismic by the river here. You can see the line set out, and then you can see Hussein here deploying a induction coil for a magnetotelluric survey. And finally, you can see a seismometer being nicely set down in a level position for a passive seismic survey. This big truck here is known as a vibra-sized truck. It basically vibrates and creates seismic waves for our deep seismic survey. You can see me operating the gravimeter for a gravity survey. And there's also some students rolling around the ground penetrating radar card for a survey. So here's our lovely TA, Brett Bernstein, pictured with a horse. And you can see a nice multi-physics approach to a survey here. You can see the ground penetrating radar card about to be pushed along a DC resistivity survey site. And additionally, here's another site of the deep seismic survey where students were deploying GTI and stride nodes to basically pick up the signals from the seismic waves. Yeah, we'd like to thank all the people who helped us get here. Obviously, the Colorado School of Mines and the Colorado School of Mines Foundation, and the faculty and everyone within the Department of Geophysics, specifically Brian Passarella and Dr. Dugan and Dr. Siegfried here. We'd also like to thank the City of Steamboat and the Routt County people and the Colorado State Land Board and a bunch of companies who helped out, like the United States Geological Survey, the Colorado Geological Survey, as well as some instructors and help from Stride, Dawson, and Collier Geophysics, and United Companies for helping us with parking the Vibe truck, Colorado Mountain College for allowing us to stay there, and Shell and the Society of Exploration Geophysics, and also University of Nevada, Reno. So yeah, now for the presentations.
Thank you. So our presentations today are going to go from kind of a small picture up to the big picture. We are reversing kind of the typical viewpoint of how we think about geology.
So hello, I'm Donald Burt.
I'm Ethan Deal.
I'm Pablo Changwan.
And for our final presentation, we worked on the sulfur cave system. And this is a snotty from, it's a cave formation that's in Sulfur Cave. And we're going to learn more about it.
So in this presentation, we're going to go over a bit of context about Sulfur Cave and why it's important to the scientific community. And then we're going to delve into the past research and how it informed our surveys that we did, which were ground penetrating radar and direct current resistivity. And then we'll be discussing a little bit of the processing flow, what our results were, the anomalies we observed in those results, and then what the final conclusions and interpretations were.
So just to position us on Earth, we are next to the city of Steamboat. And that blue dot that says Sulfur Cave, that's where our survey location is and also where the cave location is. And then right next to it is the Howison Hill Ski Resort. So more about Sulfur Cave. It is considered a national natural landmark. It was given that title in 2021. It is a hypogenic cave, which means it was formed from rising spring water coming down and carving it out. And it's formed in a travertine deposit, which is 2.5 million years old. And Sulfur Cave is considered the youngest solution cave in Colorado. Some important characteristics of it: it has very deadly gases in it, so only specialized people can go in it. And it has rare blood red worms, which are only seen in this cave. And then for research timeline, so it was loosely discovered in 1843, and then the real surveying of the cave happened in 2007, and that was more focused on cave surveying and biological sampling. And then the first geophysics presence was by Collier Geophysics, and they basically came in to look at the karst system in that area. So the Howison Hill Ski Resort wouldn't be building their large magic carpet over the cave. And then we came in Mines Geophysics came in 2022 to look at extensional features of the cave. And then our goal for looking at the cave was to look at the lateral extent of the cave.
So the first method we use is ground penetrating radar. GPR is a non-invasive method that uses high frequency electromagnetic waves to map the electromagnetic variation in the subsurface. So the basic physics and math use the radio waves velocity equation. So we take a wave regime approximation and we also put the magnetic permittivity equal to 0. We get the wave speed just dependent on the relative dielectric permittivity. So as you see, we have the GPR antenna on card, and if we have an anomaly on the subsurface, we're gonna get a parabola shape reflection because of the different distance on every point. Other important concepts about GPR that we have to take account is the skin depth, that is the penetration depth of the signal, and is inversely proportional to the material conductivity. So if you have a more conductive material, it will be less depth. The other thing is attenuation. There's the rate of decay of the amplitude, and that also very dependent on the antenna's frequency. If you have a lower frequency, you're gonna see deeper, but you're gonna have less resolution. The other one is the scattering, as shown in the graph below. Is when the EM paths deviate a lot, do a lot of homogeneities that are like less than a quarter of the wavelength. And we're using GPR method because with GPR we can map shallow electromagnetic discontinuities. And if we're trying to map the cave, we know that the electric permittivity of air is around 1, and the electric permittivity of limestone, or like the geology of the area, is around 3 to 7. So we expect to see anomalies or lateral discontinuities in the electric permittivity.
So we use the DC method as like a supplement method to GPR, because when we look at a DC survey, we see highly resistive bodies, and air is incredibly resistive. So the theory goes, if there's a void space underground and you're imaging across it, we should be able to see it with DC. So how the physics behind that goes is we chose a dipole-dipole survey, which basically takes at least 4 electrodes, and we have 2 current pumping electrodes called A and B, and we have 2 electric potential electrodes called M and N, and we pump current in with A and B. That creates a charge in the subsurface, and then we're measuring the decay in that charge in M and N. And from that, we can get the apparent resistivity, which basically takes the geometric factor and then our voltage difference that the computer measures, and then the current pumping into it. And then, yeah.
So for our GPR survey, we have it in the red dots right there that are just to the east of Sulphur Cave, like the entrance of it that's fenced in. And so in prior years, they'd used 250 and 270 megahertz respectively. So they're getting better resolution, but not as much depth as we're getting with 100 megahertz, which is why we wanted to use that and potentially get more of the extent of the cave. And so to do this, we used a 20 by 20 meter grid with half-meter line spacing, and this yielded 82 lines total. So we separate that into easting lines and northing lines, which were perpendicular to each other.
For our DC survey, noting that the DC survey line is 50 meters long, it's shown in the blue line, and then the GPR survey is shown in the red line. The DC line is running parallel to the easting lines with GPR, and we had 5 meter electrode spacing, 11 total electrodes. We did a dipole-dipole survey setup, and then we also had to pour salt water on all the electrodes because there was bad ground coupling with the electrodes, like over the cave area.
So our raw GPR data started out in time on the y-axis. And so to make more meaningful interpretations, we wanted to start by converting this to depth. So next slide. To do that, you basically have these hyperbolas that are within the data, as Pablo discussed, from anomalies. And the coefficients of these hyperbolas correspond to velocities in meters per nanosecond. So from there, it's just multiplying the depth values in nanoseconds by that, and then it converts it to meters. And additionally, we did some corrections in geolytics for noise, geometry, and attenuation. And so this yielded a processed GPR lines that we have here. And so from about 0 to 9 or 10 meters, you can see this area, a very high amplitude, very, very complex structure there. You have some areas where it's discontinuous. And then from about 10 to 17 meters in this trace, you have almost 0 amplitude, which we found to be very interesting. And then as you go past about like 18 meters, you start to get those reflectors again. And so to highlight the differences that we're getting in amplitude, we did a Hilbert transform, which essentially takes the absolute value of all the amplitudes. So whether they're positive or negative, it makes them all positive. and highlights those differences. So we use the same filters as the like the time depth slices, but we use different parameters to highlight this amplitude. As you can see here, you get that one section where you had almost zero amplitudes highlighted very well. And so we use this for products.
So for DC processing, we got a pseudo section, which is labeled as the raw DC data. And in order to get the real resistivity values in the ground, we need to compare it to an inversion model. So we used ResiPy to create this deterministic inversion. And we also corrected for elevation, so we can see the elevation profile across the 50-meter DC line. And then the depth of resolution appears around like 2.5 meters.
So with that Hilbert transform, we were able to generate these amplitude slices to illustrate that in a 2D map view. And we didn't use 0 meters. In GPR, there's a wow signal, which is caused by the source to receiver, and that has a lot of noise in it. So we had to throw that out. And then from 7 to 8.25, as Pablo discussed, like the skin depth, we just had a lot of noise and the SNR wasn't very great there. So this shows that we have a very low amplitude anomaly that gets larger with depth from, you can see more in 2.5 down to 6.5. It also pinches out as you move from west to east.
So for our DC results, our original inversion, we saw that really resistive body like right underneath where the road was. And so we thought, well, maybe that resistive body is actually blowing out any type of like other anomalies that have lower resistance. So we created another inversion model where we just maxed out the resistivities at 1,000, and we started to see 2 additional anomalies, one being on the top of the hill around like 50 meters, and then one being at around a depth of like 4 meters and closer to like that 35 mark where the cave was. And what's really interesting is that that resistivity value is around the same resistivity of limestone, which travertine is very similar to limestone.
So we put all the anomalies together in one map. We have the GPR slice anomaly at 2.5 meters depth. We have the DC anomalies on a line. And we also added the Collier anomaly of the survey done in 2021, where they thought the cave was. We have a road anomaly on the north side of the map, where you can see that DC says that there's a resistivity anomaly. The GPR is saying that we have in that same section low amplitude anomaly. The width of that anomaly is parallel to the anomaly is parallel to the road, and the width is around 7 meters. And we also know that anomaly is pinching out from west to east at around 13 meters. We also have the other cave anomaly on the south side, and with that we know that in DC we found other less resistive anomalies, and in GPR we found a lot of reflectors and the structure and more structured than in the rest of the readings. So although we were not able to completely map the lateral extent of the cave, we were able to divide all the anomalies into 2 sections on our map. So we have first the section 1 that is on black, and we have the cave anomaly. In GPR, we can see the cave anomaly on black has more reflectors and a deeper resolution. We have more scattering, which show that there's more things, more structures, and more discontinuities on electric permittivity because of the different materials. We also know that it is a conductive part because of the DC line that is around 15 ohm meters resistance. And we also have these other 2 anomalies to the south that shows that there's to the south more resistive anomalies around 800 ohm meters. That is very close to limestone resistance. We also have the section number 2, which is along the road, and this is the road anomaly. In the road anomaly, we see more shallow features on GPR. We see a lot of we don't see much reflections or readings through it. And we have also a resistive anomaly from the DC line that shows a resistance bigger than 3,000 ohm meters.
Thank you. Are there any questions?
We have 2 minutes for questions.
Great presentation, by the way. I'm wondering why you chose GPR with DC together.
So I think with DC, the thought process was, as Donna discussed, that the resistivity of air is so high that we would see a highly resistive anomaly and then be able to use that to see where the GPR is. So we could geographically reference them and then use that to interpret the GPR data more effectively.
We have a question from the online audience.
Of course.
What is your recommendation for follow-on geophysical investigations for the 2024 field camp participants?
We would recommend that they, one, they choose a grid that's more positioned over the cave, and that they also use 2 different antennas. So we use the 100 megahertz antenna. They should also use the 150, or sorry, the 50 hertz. The 50 hertz antenna, so you can actually see possibly see the bottom of the cave.
Yeah, I would also say adding more DC lines in conjunction with your GPR, maybe not that fine of spacing, but just do like a grid of DC. And I think that would be really useful for interpretation. And I think 150 combined would give you really interesting resolution. I think as you saw, this resolution on this data was really fantastic. So.
And also staying away from the road. Yeah.
Thank you again. Yeah. Here's my there. Up next, we'll be going one size up and looking at cross fault geology right in downtown Steamboat Springs using transient electromagnetics.
Good morning, everyone. My name is Victor Ogi,
My name is Ilkohan Angiri.
and today we're going to be presenting on our interpretation of cross-fault geology in the Steamboat Springs area using transient electromagnetics.
Our agenda for today, we're going to start talking about discrepancies in steamboat area geology. What is transient electromagnetism, survey design and processing, results, analysis, and interpretation, and lastly, summary.
So despite the fact that Steamboat Springs is a relatively popular tourist destination for outdoor activities, the geology of the area is not particularly well understood. So on the map here, the red line indicates a known fault that transects through the western edge of downtown Steamboat Springs. The football on the eastern portion of that fault displays geologic formations that are around 1 million years old, while the hanging wall formations are around 100 million years old. So this was one of our first motivations. We wanted to better understand what about the presence of this fault may be contributing to that drastic difference in formation period. Second, the blue stars here note mineral and hot spring formations in the Steamboat Springs area. And so previous research has shown that the mineral and chemical compositions of these springs are drastically different. And in some cases, they're no more than 10 meters apart. And so we really wanted to understand if the fault may be a contributing factor in the discrepancies in those springs. And if so, what about the fault may be causing that? And then you'll notice the black dots on here are our TEM site locations. So it's where we actually conducted our surveys, and they're on both sides of the fault. So we're able to compare the geology on the hanging wall and the football side. So first, I'll just talk a little bit about survey design with TEM, and then I'll talk about the physics of TEM and how we get the information that we're after. So first here, if we look at the left panel, the orange box there is what's called a walk tem, and that's kind of the brains of the operation. It's what's going to produce the current that we need, and it's going to record the signals that our receiver picks up. So the red loop here is the transmitter cable. What happens is the walk tem produces a current that it sends through this cable. And that current is going to induce a magnetic field around it, which is denoted by these vector lines here in yellow. That's our magnetic field. And you'll notice that it's propagating into the subsurface. So now, once we turn off our walk tem, the current ceases. And what's denoted here in the middle panel, those orange lines are what are called eddy currents. And so eddy currents are produced by that magnetic field, and they're going to propagate deeper into the subsurface. And so you can kind of think of them like smoke rings, where they start off small, and as they travel further, they expand. That's essentially what's happening here. And then on the third panel, those eddy currents are going to induce a secondary magnetic field. And that's really what we're after. So that secondary magnetic field displays property of the material through which it passes. And so from that, we can invert to find the resistivity of the rock beneath us. And so you'll notice there the middle coil is now highlighted, and that's the receiver coil. That is what is picking up those undulations in the magnetic field and reporting it back to our walk tem.
To start processing the TEM data, first, we should import the data file from the EBM WACTEM and open the GDB file in SPIA software. Noise and spike filtering are done automatically. Our goal here is to reduce the misfit between the predicted data and observed data. We can do that by changing the resistivity and depth of the layers we have on the model, and we can do that by shifting the green line segments either vertically or horizontally. On the right figure, we have a better and accurate results, and we should run the inversion now. Here we have initial inversions. The first project is project 27, located on the hanging wall. We can see that there is 2 layers. The first layer starts from the surface to around 32 meters with resistivity value of 15 ohm meter. The second layer from around 32 meters onwards with resistivity value of 45 ohm meters. Also on project 40, we have 3-layer structure. The first layer from the surface to around 6 meters, from around 6 meters to around 70 meters, and from around 70 meters onwards. And we have different range of resistivities as we can see here. Also, the green line represents the reliable depth of investigation in our case.
So once we're able to produce individual inversion results at each station where we collected data, so you might remember the fault that we showed at the beginning. So what we've done here is we've split one group into all inversion results from the hanging wall and a second group into all inversion results from the footwall. And then we've taken an average over all those results. And that's what's displayed on the left and on the right. Hanging wall results on the left, footwall results on the right. And so on the hanging wall, we can denote, or we can see a very clear layer at the beginning from around 0 to 16 meters below the surface. And that's going to have resistivity values between 20 and 30 ohm meters. Underneath this, we have a second layer with resistivities between 30 and 40 ohm meters, extending down to 100 meters, which is about where we're no longer able to discern our signal. On the footwall, we have a primary layer at the top there denoted by A, and that has resistivities between 40 and 50 ohm meters, and it extends down also to around 15 meters in the subsurface. We have a secondary layer that follows this that's between 10 and 20 ohm meters, and it extends down to 79 or 80 meters. And then we have a third layer that follows this with resistivities between 20 and 30 ohm meters. And so you can see here that we're already starting to form some interpretations about our geology. But we want to do further analysis to understand some effects that may be showing up that we have not accounted for yet. So we're going to first try to categorize all our rock types by resistivity. And so all of our values were in a range of 1 to 100 ohm meters. And we know from literature that all of these rock types have specific resistivities that they're associated with. And so we can go through and try to say, oh, that looks like a sandstone based on its resistivity value. You might notice the conundrum now that we're facing. There are a significant number of rock types that could be displaying those resistivity values. And so we know, for example, that it's not sea ice because there's not sea ice in the middle of the Yampa Valley. But it could be shale, it could be sandstone. We know that there's a coal mine in Craig, which is less than 50 miles away. Could be coal. The shallow MT group may suggest later that there are clays in this area. So we needed to do something else to get a better constraint on what we might be looking at. And to do that, we did a water saturation analysis. So RT's equation relates the water saturation in the ground to our measured resistivity, which is denoted by RT there in the equation. And so this function is a parameter of porosity of the material as well as the resistivity of water in the area. So the resistivity of water actually changes where you go, and it's dependent on numerous things. But to estimate our value for the resistivity of water, we looked at historic USGS data for the amount of suspended particles in the Yampa River and the average river temperature in May. And so from that, we were able to get a representative value of around 1 for that resistivity. And then we know that A, M, and N are constants that we can approximate. So what we do is calculate our porosities. And so now instead of having a problem that's constrained by one parameter, we have 2 parameters. That second parameter being the porosity of the rock. And this also is a water corrected porosity. So we're accounting for the water that we believe is present. And we know from field observations that the water is there because the water table is often at the surface and we can see water bubbling up. So we have our resistivity value denoted by RT and our porosity denoted by phi. And from these 2 things, we're able to make a much stronger interpretation of what the geology might be.
For the interpretation, we suggested that the hanging wall has two-layer structure. The first layer is sandstone shale, and it's from the surface to around 15 meters. And the second layer is shale from around 15 meters onwards. On the other side of the fault, the footwall, we suggested that there is three-layer structure. The first one from the surface to around 30 meters, which is alluvium, and from 30 meters to around 80 meters, we have sandstone shale, and from around 80 meters onward, we have shale. Also, we suggested that the layers B and C are highly correlated to each other on both sides. For summary, we suggested that there is two-layer structure on the hanging wall and three-layer structure on the footwall. And also, we're confident that the water saturation analysis help us to constrain the lithology and geology interpretation. Alluvial deposition may control the composition of mineral springs. Lastly, we have recommendation to test the water properties in the area that may affect the local surveys and complementary seismic survey to constrain the lithology in this area. Here is our references.
Any questions or feedback?
We have about 5 minutes for questions.
So I'm assuming that you've limited your version to have a specified number of layers on each side of the fault.
Yeah, so we're able to, as she mentioned previously, we can adjust our prior model so we can add layers or subtract layers. So we tried layers with values between 1 and 3. And what we noticed is that 1 and 4, layers 1, 2, and 3 typically had the best data misfit for our prior model. So it reduced the data misfit most. And so we ran 1, 2, and 3 layer models for all of our stations. And what we found is that 2 and 3 layer models respectively for the hanging wall and the footwall side showed the lowest standard deviation in our results.
So I guess my main question is, how did you decide to start with 4 layers?
Trying to experiment. Yeah, we're trying to experiment the number of layers, and we saw that after the inversion, there is a table with numbers and there is standard deviation values. So if you chose, let's say 4 layers for the hanging wall, we would have a standard deviation value of 99. So we started to decrease the layers, and 2 layers was the best standard deviation values. We have values under 2.
The WalkTem also automatically produces a single layer inversion model. And so a prior model, and then it produces inversions from that. And so we could kind of get an idea from that how many layers it was picking up. So like we knew there weren't going to be 15 layers because the automatic inversion done by the WalkTem suggested 2 or 3 for almost everything.
Can you go back to where you had the 2 locations?
What?
The 2 locations that we actually have the station. Okay, yeah, sorry. Okay, yeah, so you're pretty close to where all the springs come out. It's right along that fault, right?
So there's a large cluster of springs right in here where the fault pinches into the river, and then Cave Spring, so Sulphur Cave Spring, I believe, is right up here. But there are no springs right along this western slope of the fault.
So considering that there are geothermal waters possibly coming up along that fault based on your station being between Sulphur Cave and the other here. I'm curious why you selected Big Yampa to use as your water source.
Sure. So we played with we looked into a lot of data, and the Yampa River data was, we were able to get a water resistivity value from that with the most accuracy. So we looked at some of the information from the Cave Springs, but it was difficult to, so we used a Schlumberger waterlog table, and we needed very specific part per million count of solved material from that, as well as temperature. And so most of the sites were located, this is the Schlumberger table that we used. And so you can see that it's a function of temperature and dissolved content. And so the information we were able to get from the Yampa River stream gauges allowed us to most easily use this table.
So do you think it would affect the results if you use salt?
Yes, because there should be a higher concentration of dissolved particles in there, and so that number would be, our resistivity of water would be brought down, and so we may actually end up seeing lower porosities there, which would still suggest the materials that we suggested. If we, for some reason, started getting water resistivities that were 100, then we would be interpreting something different. So more dissolved content would mean that our porosities would be lower, and therefore our conclusions would still be the same.
It looks like you collected multiple data points on those sides of the fault. You're showing interpretation two. Why those two? What happened to everything else?
Nothing. So those were just two that we wanted to show. So these are the SPIA inversion results, and we just wanted to give an idea of what we were first looking at. Because we had to get to know SPIA and then how to get our own inversions out of it. So these are just two representative examples. But everything else from this point on, we use those average inversions from the football group and from the hanging wall group. So there's nothing in particular that is special about those.
Eileen, is your question short?
For your seismic recommendations for next year, based on what data was collected last year, this year, what do you think is like a good spot for us to go and try and look for maybe the same basis that you?
I would probably stay away from the cave because we know that there's some interesting geology going on there, but it's probably not representative of that entire football side. And so I would also suggest staying away from the river because we had a lot of difficulty with the water saturation issue. So anywhere that's a little drier at the surface would be good. And more stations on the east side and not the west side. We have plenty on the west.
Thank you again. So one thing I do want to know is for any geophysicists in the room, you're well aware that one of the big features of being a modern geophysicist is data wrangling and data documenting and data provenance. And this group that worked on the TEM did something remarkable that I'm impressed could be done in 9 days, which was use last year's data. And so that meant the field camp last year had to document their data well enough that they could go in, download it, and know what was going on. And that, I think, inspired them about data documentation for this year. And so they're learning some of these, how do you finish a project such that someone else can take it on? Those sorts of skills that are really hard. It was very impressive. Up next, we're sticking with hydrogeology, but we're going to go a little bit broader in the region.
Hello, my name is Jackson Howard. I've already met my colleague James. And for our project, we specifically focused on the hydrogeology of the Steamboat Valley North Park Basin based on the increase of population and desire for a better understanding of the hydrogeology and general geology in this area. So before we start, I'd like to acknowledge some of our colleagues and sources at the USGS, specifically Dr. Ben Murphy, Dr. Jeff Pepin, and Dr. Chloe Gustafson, who assisted us greatly in our research, as well as the State Land Board in Routt County for giving us permission to work in these spaces. So our primary problem that we're looking at is focused on the 87% population increase from 1990 to 2020 in the Steamboat Valley. With this increase in population, we've seen rapid urbanization in the areas, which is intimately connected with the local hydrology of the area, as in that community, for instance, there's lots of hot springs, there's the Yampa River, both for recreation, as well as an economic aspect of the hydrology in the area, such as using the water table to support cattle ranching and timber in the area. So our primary motivation for working on this was to better our understanding of the North Park Basin and Steamboat Valley, both basins up in the north central portion of Colorado, which has honestly had very limited discussion and to research prior to us coming up there and starting to look more at the local hydrogeology, as well as wanting to better create new hydrogeologic models in that area compared to some of the prior models that had been established. So for instance, in these previous models, there was the general idea of there being a permeable rock layer, probably around 3 kilometers in depth from the surface, with a crystalline basement layer underneath that. So in the Steamboat Valley area specifically, we were thinking that there would be cycling of the water through that permeable layer before reaching fault lines and coming back up in the form of hot springs. So we would also like to think about using our research as kind of a ground level start to future research in the area due to the already limited nature of research on this topic. So for our primary method, we ended up using magnetotelluric, or MT for short. This is basically the measurement of local waves from surface magnetic fields and surface electric fields. So using these two, you can get a general sense of subsurface resistivity structures. This method ends up using local fields that have been produced by a much larger background field, typically in the form of magnetosphere activity and electric storms across the world. So for our data collection, we ended up focusing on 3 sites around the North Park and Steamboat Valley areas. We had 2 of our sites in the North Park Basin, with a 3rd to the lower southwest area on this map, which was closer to the Steamboat Valley. This North Park Basin up in the area is surrounded by the Park, Medicine Bow, and Rabbit Ears ranges, kind of its own little self-contained area with, out of this picture, the Steamboat Valley. So here's some more information about our sites. We had CO 702, which was closest to the population center of Steamboat Springs, along with CO 704 and CO 701, both further out into the North Park Basin. You'll see further in this, presentation that we focus more on CO 702 just because of its close proximity to Steamboat Valley itself, which is again the main population center of that area.
All right, yeah, let's get into looking at the data here. So we spent 3 days collecting data at site 701 and 6 days at site 702, roughly 2 days at site 704. So these 3 surveys basically output what's known as the magnetotelluric impedance matrix, and impedance, excuse me. And you can see that matrix in the top right corner. From the off diagonal values of that matrix, we're actually able to obtain resistivity, rho, apparent resistivity, as well as the phase or feet. And these are crucial for what we really want, which is making geological interpretations. Within the data set, so we had an apparent resistivity and phase measurement at a series of different frequencies. And it's important to note that this resistivity was in log-based values. So yeah, our goal was to get the data and manipulate the format of it so that we would be able to run inversions with it. We used Dr. Daniel Blatter's MATLAB script in order to run a one-dimensional Bayesian inversion. And this inversion had 100,000 different iterations focused on finding the most likely subsurface structure. So it's sort of probability based. You can see in this figure here, we have our resistivity and phase versus the period. And the red dots are the actual data points that we collected with their respective errors. And behind them, you see all these gray lines. Those are all the models following it. So you can see the models fit the data very well. And we ended up plotting our inversions of depths of 0 to 4,500 meters and with resistivities of 0.1 to 1,000 ohm meters. So now we're going to look at some of the results of these inversions. You're looking at posterior probability density functions. Obviously, you have depth on the y-axis and resistivity on the x-axis, and the color bar is representing essentially probability. So the closer to yellow, the more likely that these resistivity values are to be correct. And additionally, you see the two red lines. So the red line on the left denotes the 5th percentile of the models, and the red line on the right denotes the 95th percentile of the model predictions. So within those two red lines, all those resistivities is where 90% of the models predicted data. So we'll look at 701 a little bit. It appears to be pretty uniform until about 1750 meters of depth, where you start to see a roughly 0 ohm meter resistivity material emerge. 702 we thought was the most interesting because of this very apparent change in resistivities. So from about 0 to 750 meters, you see about a 10 ohm meter resistivity material, followed by a quick decrease and a somewhere between 3 and 5 ohm meter material for the rest of the plot from 750 meters to 4,500. And 704, which is relatively very uniform all the way through, with about 10 ohm meters resistivity values. So yeah, let's dig into 702 more a little bit. So using this resistivity and lithology chart, we determined that the low resistivity or the higher resistivities from 0 to 750 meters are likely shales lying in that 10 ohm meter range. And below that, we believe that the lower 3 to 5 ohm meter resistivities are water saturated clays. And this is important because it actually differs quite a bit from the United States Geological Theory's original, United States Geological Survey's original theories at this site or this area. So now we'll look at that a little bit. So we used the application called SimPeg to run a one-dimensional MT inversion. And we plugged in the USGS's estimations for that area. So we have a 100 ohm meter material until about 1 kilometer or 1,000 meters deep. And it was believed that there would be a large rise in resistivity at about 1,000 meters up to 1,000 ohm meters. And you can see that in their resistivity and phase plots. When compared with our data, we never saw that large or highly resistive area. And please note also that USGS graphs are in frequency on that x-axis, while ours are in phase, but they're inversely related and they're inverse values. So that all matches up. We don't see any spike, any true spike or decrease in the resistivity throughout our survey, and we really don't see much change in the phases, both for the X and Y and YX directions either. Some possible sources of error. So because we ran a one-dimensional inversion, we needed to assume that the two directions of both of our apparent resistivity were, they should be basically on top of each other, the data from those. So you see the X, Y, and YX direction data. And you can see towards the lower phase values, they sort of differ a little bit. So this could have caused some error within our inversions, especially with the very shallow depths. And additionally, we used a 5% error floor for both apparent resistivities and phases to account for uncertainties in dipole length and azimuths from the survey. This was sort of an estimation and not necessarily the most accurate percent error, but we stuck with it as it's common practice within MT. So yeah, our conclusions, we really did not pick up any highly resistive material below site 702. And we believe that all these clays are actually acting as a cap rock for the water beneath the surface there, that they're not rising much at all over there. And they're continuing to flow east towards the faulting systems where the springs come to the surface, and they're likely rising up to the surface there. And yeah, there's just a whole lot more science to be done here, and we'd like to see more geophysical surveys at site 702 in the greater Steamboat area in general in the future. Thank you.
Questions?
looks like you're not possible in the static shift here. Three curves with that parallel offset. Curves, you guys looking at correcting that at all? How effective is also maybe something.
No, we did not look into correcting that. Yeah, signed a note.
Yeah, basically, when you get the parallel offset like that, that just means there's a difference in the electrodes locally, so you get the parallel shift of the curves. Typically, the top one or the bottom, right? I saw you very much. You see how it affects the results of the inversion of the TE.
They've had 8 days with this data.
No.
Yeah, that's a great comment. I should also add, before we throw it to a question from Iga, that their final written presentation of this data is not due until tomorrow. And so they're going to be integrating the answers to all of these questions into their work. Iga?
Methods to address your hydrology question. Why did you choose MT?
I would say we focused on MT because it was interesting that this is some of the first research that's been done in that area for magnetotellurics, as well as it's much less invasive than, say, large seismic surveys. Feel like it can also get to a much deeper depth. We can find more data much deeper than we focused on in our survey. I guess recommendations for further studies in the area would be possibly focusing more MT surveys within Steamboat Valley itself, closer to the Steamboat Springs sit town. While that might give some error due to noise, that would be much more interesting in looking at the specific hydrogeology related to the faults in that valley.
And I think 702 would be a good spot for a hammer seismic survey. Also. Yeah.
Just a quick question. Am I correct in thinking that your 3 sites coincide with the fault that was presented in the last project? Or
No, do they coincide with the fault? We didn't.
the same site location?
No, these are not. These site locations we worked on were primarily focused on deep seismic or deep MT, excuse me. So we just kind of piggybacked onto those, took data from those sites that were available to us and went from what we had.
Thank you again. As Jack alluded to, these sites were actually deployed to look even deeper than the 4.5 kilometers that they looked. And so this group will be telling us about the deeper crustal structures in the area.
So hello everyone, I'm Hussein Khalid. I'm Colin Thomas. And for our project, we were using magnetotellurics to speculate on a long debated question of whether the Rio Grande Rift extends north of where it's super obvious at the surface. So yeah, the Rio Grande Rift is basically just an area of the crust that has a lot of extensional strains kind of moving apart, moving away from itself. And geologic features that are really common with this at the surface are called horse engravings, where basically the gravens are kind of like valleys and the horse are hills, and you get them stacked up next to each other and the stress works to the system. So yeah, this is the San Luis Valley down here, the upper Arkansas Valley up there, the Sangre de Cristo and the 10-mile ranges, which are clear expressions of the rift at the surface. And we were looking up there in that white square to see if we could identify any features further lower in the crust that would indicate that extensional strain continues in that direction. So why MT? Why not any other geophysical survey? So first of all, we need to go back to the Rio Grande Rift and what geological and physical features it would cause into the subsurface. So the rifting would cause an increase in permeability and some partial melts would go up into the subsurface. So those two features would cause an increase into the conductivity of the area. So we decided to go with MT since it's a great method to measure, to map deep down the earth for conductivity. So MT basically works by having a change in the magnetic and the electric field. So the change in the magnetic field would cause an induced current into the earth. The current would travel through some conductive, some resistive materials, and that would cause a change into the electric field. So with measuring all of those, we would be able to have a conductivity model that would help us interpret the data. Something to notice that the sources of the changing in the magnetic field would be the solar wind and the lightning, and those changes over time. So we would be able to measure different things at different depths for conductivity. So in this field camp, we focused in going through 4 main sites to do our surveys at. It's in the red circle in here. So we went in there and gathered data from those 4 sites. It was in the duration of the 2 weeks of the field camp. So the survey that was there for the longest time was around 6 days, and the shortest was around 2 days. The other data that we used was supplemented by the MTRA, USRA, and the USGS. We used other 15 sites to interpret our data. So for the survey setup, we had 4 electrodes, 3 induction coils, and 1 data logger. So we had the electrodes in the cardinal coordinates, and we had 2 of the coils in horizontal directions, one facing north and the other facing east, and we had 1 vertical coil. All of those were connected to the logger. After we got them connected to the logger, we ran some calibration, some receiver calibration, and some source calibration, and from that, we were set to go and do the survey. So for the processing part, we did an initial processing using EM power. So as you can see in the top left there, the raw data in the time domain, we took that and we did a windowed Fourier transform. So we had windows of 3 hours done in Fourier transform. After we did the Fourier transform, we did some quality checking on the data. So the noisy data, we got rid of the noisy data and we had the smooth data. After that, we remote referenced the data from different sites together, the sites that has the most time overlapping, and did some coherence filtering, and we got the final result or the final result from the initial processing, as you can see in the bottom in here. So this data is kind of like smooth data, doesn't have much noise, and we're set to do inversion.
After processing, we've done 3D inversion in order to have 3D results. And the basic theory behind our inversion is that we used full impedance tensor, denoted as Z. And we also used vertical magnetic field transfer functions, denoted as VTF, using data from 19 different sites distributed across north central Colorado. We inverted both the electrical field and the magnetic field in order to have the impedance tensor as shown in this equation, where the impedance tensor has 4 different components: ZXX, ZXY, ZYX, and ZYY. On the technical side, we did 3D inversion using the mod-EM software, and we had a cell size that is constant in the horizontal with 5 kilometers, and that is increasing graphically, and the vertical starting from 100 meters at the surface and reaching 7 kilometers at depth of 50 kilometers, with a maximum depth of 900 kilometers. We also tested various acceleration smoothing factors, namely 0.2, 0.3, and 0.4, and it shows the 0.3 one, since it was the most robust one in terms of clarity and easiness of interpretation. We covered period from 1 second to 10,000 seconds, and the longer the period is, the more you can see into the ground. Also, we got a normalized roots means squared error of around 1.46, which is considered reasonable in terms of the depth we're looking at. It means that most of the characteristics of the data were captured. The figure here shows the 0.3 model that we worked on. And the coloring of the map itself is actually based on the conductivity values, dot conductivity values in Siemens per meters. And the lines you're seeing here are actually 71 meters resistivity contour lines, and they're varying in color based on their depth, as seen in this color vision. And our model showed the various important findings. First, we've seen that the conductive tracks in the lower crust are actually extending towards the north, towards the region of study here. And that actually confirms the hypothesis that the Rio Grande Rift is extending beyond areas of clear surface expressions of rifting. We also found this conductive type here is relating the area of study all the way to the zero crater, which is a volcanic activity that took place 4,000 years ago. That actually is a compelling evidence that relates the Rio Grande rifting to recent volcanic activity. Lastly, we've seen conductive tracks up in the north around Wyoming borders. And the one right across the north of the region of study, we know that it's related to the Cheyenne Mountain Belts conductive activity, conductive nature. But the one in the northwest of the map, we're actually not certain of. It can be related to the Cheyenne Mountain Belts as well, but it can also be related to the Rio Grande Rift, and further studying needs to be done in that area. This map here shows an east-west cross-sectional conductivity map passing through steamboats, and the coloring map also here is similar to the last one. When you look at the graph, we can see that around depths of 50,000 meters, which is around 50 kilometers, you can see between the area of Steamboat Springs and North Park that we have conductive tracks, and those are actually related to the conductive tracks we talked about in the previous slide. You can also see in this map conductive tracks shallower, around 10 kilometers of depth, in the area of Yamba volcanic field. And that's actually can be related to the subsurface geologic activity, and can also be related to the Rio Grande Rift. However, there is large uncertainty in that area since there was not enough MT surveying done in that area. So we would suggest further surveying in the area west of Steamboat Springs.
Yeah, this is the same map that was on the other slide. But basically our core conclusions were that the lower crustal conductive tracks that had been found in previous studies do extend north into the region around Steamboat, as Solomon said, supporting the hypothesis that the Rio Grande extends up to the area. And then also the fact that this conductive pipe can be seen going from that track to the Zero crater is evidence that this eruption that was only 4,000 years ago is likely a result of Rio Grande drift activity. And then, yeah, just to point it out again, this more conductive area to the northwest of the study area could be Rio Grande related, but it's right next. I mean, certainly that part that kind of trends east-west at the very top is because of the Cheyenne mountain range, which is just naturally conductive. But as far as the north-south trending stuff that goes south of that, there needs to be more data to really constrain that better.
Time for a few questions.
That was a cool presentation and some neat work. Thank you. Curious what other geophysics, or I guess anything, I guess you might do to try to further confirm or what you've shown.
For the case of our study, we need the surveys that penetrate deep down the earth. So having maybe deep seismic could be a good idea to correlate both of them together and see what's the result. Because you're looking for conductivity features, which is more EM. Yeah.
However, seismic is pretty sensitive to things that are more liquidy versus things that are more solidy. So it's a pretty natural combination, but it'd be deep seismic than what Field Camp does, but it'd be a pretty awesome survey. Thank you. Maybe I'll add that's, of all the things I've ever seen coming out of Field Camp, that's probably some of the more regionally significant of all the results that I've seen.
Do you notice a difference in data quality depending on how long you observe at a specific location?
So The longest location that we had was nearby some pipelines and some utility lines, so it had some sources of noise. We cannot say if having them longer would affect the data, but I think having out of those factors, it would be less noisy.
We have a question online. Can the group elaborate on the choice of the model cell size for their 3D inversion? Do they think the 5 kilometer cell size in the XY dimension is reasonable compared to the MT station spacing?
Yeah, so I can't speak a ton to how well it relates to station spacing. The rationale behind the model, the grid spacing of this inversion was that we needed something quick. Didn't have a ton of time to do it. The USGS was kind enough to let us use their supercomputer, and it takes a while. So we were looking for something that would be fine enough to point out the features we were looking for while also being coarse and small enough that the inversion wouldn't take super long.
We actually had a bigger inversion of 81 stations that were running, and still it is still running. So we didn't have enough time to run a bigger grid. So
you've had the data for 8 days. How long did the inversion take?
The smaller one took a single day. I think the bigger one was going to take a couple days. So yeah.
First of all, nice job, y'all. And perhaps this is the nicest question, but kind of like you were interpreting some of the northwestern corner that showed up in your inversion. Do you have any feelings about whether or not there could be like an edge effect of your algorithm running?
So that was with the edge already removed.
Okay, great.
Right, that was just the core plotted. Yeah.
Whether or not that was like the edge of your grid.
Yeah, no, so the model extended beyond what was plotted. We just included the core.
Thank you. And to bring us home, we'll have a talk comparing two different types of instruments.
Good day to you all. My name is Mohammed, and with me today,
Hi, Hamad.
we are absolutely thrilled to present an answer to a very interesting question. Why pay 1,000 times more to capture an earthquake signal when there are cheaper and easier to deploy instruments available? Before we start, we'd like to express our gratitude to the people of Steamboat, Pascal, the GTI, the GP department, and all faculty and staff who made this field camp possible. Special thanks go to our primary mentor, Dr. Jijin, and Dr. Aaron Girard for their continuous support throughout this project. Our main objective today is to see will this noisy nodal geophone, which is shown in red, can capture an earthquake signal. In this figure, we show the raw data for the nodal geophone in red and the seismometer instrument in black. As raw data, there's nothing much to see in the nodal geophone except for a lot of noise. However, in the seismometer, even as raw data, we actually can see the P wave clearly.
So in this presentation, we will begin by introducing the topic of signal collection and discussing the instrument we employed during the field. Then we will shift our focus to the methods section, elaborating on the techniques we utilize to gain more insights about the data collected. Following that, we will present the results we obtained and engage in thought-provoking discussions just to uncover their meaning and implications within the scope of our study. Finally, we will conclude by summarizing the main points covered. So let us get started. We would like to start to give some background on the earthquake we are analyzing. First, the earthquakes happened near Panama and with 13-kilometer depth and 6.5 moment magnitude. The red star here shows the epicenter, and the blue triangle here shows the location of the instrument we employed back in Steamboat. However, before we dive in all of the experiment details, let us experience the earthquake itself. This should give you an idea about the high energy released at compressed time. Now, since we know what we are looking for, let us talk about how can we record that data and see it. So in the field, we use 5 instruments, but for our presentation, we only analyzed 2 instruments. First, the CMG3T broadband sensor, and it is a reliable and high sensitive instrument developed by Pascal. It operates within a wide frequency range, capturing seismic waves across different frequencies. They can detect a broad spectrum of seismic events, including both high and low frequency waves. However, this comes on the expense of deployment and price. It requires time and effort to deploy it. As we can see here, we need to dig a hole, level it, and so on. Next, we deployed an N3 node, geophone node co-located in the CMG3T seismometer. The N3 node is a cutting-edge 3-component developed by GTI. The N3 node is equipped with 3 sensitive geophones that measured ground motion in 3 component directions. Enables to the detection of seismic waves in multiple dimensions. As you can see from this slide, the geophone is smaller, which makes it easier to deploy in some remote areas and challenging terrains. Also, the cost effectiveness of the N3 node is also a noteworthy aspect, because it provides high performance seismic monitoring with competitive price.
Now, let us cover what we use in processing. We use several techniques to analyze the seismic data. First, we remove the mean and linear trend, so our data will not be affected by long-term variations. Then we apply the bandpass filter from 0.1 Hertz to 1 Hertz to help us focus on the frequency range of the earthquake and remove noise or interference. Signal-to-noise ratio was assessed using the root mean square method. This allowed us to quantify the ratio of the signal to the noise, providing insights into the quality of the recorded seismic data. Additionally, we use the Fourier transformation to transform the seismic data from the time domain to the frequency domain. This enabled us to explore the spectral characteristics of the seismic signals. Now, it is time to see how our plot from the objective slide will look like after processing.
Now let us see the exciting part, which is results. So these 2 figures display the time domain waveforms for the vertical and north components after processing. And the legend, the black line represents here, the black line represents the signal captured by the CMG3T seismometer, while the red line corresponds to the N3 node. Additionally, the blue line here at the beginning of the figure represents the origin time of the earthquake, followed by the second blue line, which is the P wave, and finally the red line, which is the S wave. So observing the figure, it is evident that the CMG3T seismometer and the geophone align perfectly in capturing the P wave, as you can see here. However, when it comes to the S wave, the CMG3T seismometer provides a clear representation here. We can see the seismic event. However, for the N3 node, it is not that precise and clear. So why is this true? This is true because seismometers are typically better suited by capturing low frequency waves like the S waves, for example, and geophones are designed for higher frequencies.
Moving from the time domain to the frequency domain, we start from the much lower frequency in the far left side. The red line represents the nodal geophone and the black line represents the seismometer. For frequencies lower than 0.1 hertz, they diverge because the seismometer is sensitive to low frequencies, while the geophone is not. However, as we move to the right up to 0.3 hertz, things get more interesting. We can see that at this point, the frequency spectrum from both the geophone and seismometer start to match. This implies that the geophone can actually be sensitive to signals lower than 2 hertz. The next slide will examine whether the observed data in this spectrum is actually noise or signal.
So the signal to noise ratio provides valuable insights into the performance of the CMG3T and the N3 node. Here we can see a black dashed line, and beneath that there's no signal. So remarkably, both instruments exhibit alignment from 0.3 hertz, approximately here, and higher, which is a significant finding and proves that this is a signal and not a noise. It demonstrates that geophone nodes have the capability to capture signals at frequency lower than 2 hertz. This outcome is both interesting and impressive, as it expands the range of seismic data that can be effectively captured and analyzed using geophone nodes. The alignment between the two instruments further reinforces the reliability and effectiveness of geophone nodes for seismic monitoring in a wider frequency range.
So let's conclude this. The key takeaways from this presentation are: geophones are actually capable of detecting the P wave from an earthquake starting from a frequency of 0.3 hertz. This means that we can use them for early warnings and global tomography, as they are cheaper and easier to deploy. However, geophones cannot capture S waves or surface waves because these reside in a much lower frequency spectrum. Therefore, we still need seismometers to capture such signals that are in the lower spectrum. And that will be it.
We have a couple of minutes for questions. Ethan.
So for earthquake monitoring, do you think the broadband seismometer is worth the price tag and installation time compared to a regular geophone?
Well, if you have the money, definitely.
But you can capture seismic events like the P wave with the geophone. So it depends on what you want to capture.
That's indeed.
What about amplitude units out of your plots? Are you actually comparing instrument corrected data, or were you comparing your own data after filtering?
You rephrase your question?
So when you measure motions on seismometer or on geophone, typically it's voltage or digital count. Have you made a conversion to unit of motion like particle velocity meters per second or something like that?
No, we had some trouble removing the instrument response from both of them. So we left that out for future work.
Do you think that including that response correction would perhaps change your conclusions a little bit?
Further discussion with our mentor, that could be a reason, but we do not expect that to happen. However, in future work, we're probably gonna do that and update our conclusions based on our future.
Okay, 9 days.
8. Tomorrow's day 9. Eileen?
So you mostly focused in on this teleseismic event for around Panama, But were there any events in Colorado or neighboring states during that time where now that you've kind of identified 0.3 hertz and higher as the range where you think you're getting okay signal, where you could kind of redo the analysis for, S waves at higher frequencies from closer?
So this was the one that we showed. This was the nearest earthquake that happened during the days we employed the instrument. That's why we chose it. And yeah. And for future recommendation, we will do that for other earthquakes. So
You have a question online? Well, you have one comment, one question. Gavin Wilson says, fantastic to see a presentation on instrument comparisons. Roy from Collier Geophysics says, very interesting work. Did the group compare the other horizontal component of the two seismometers to try and ID the S wave in the GTI node?
Yes, it was the same conclusion. Any other questions?
Sure. So the 1,000 to 1 is a pretty large price difference. So let's suppose you had some kind of middling amount of money and you could maybe buy a whole slew of nodes, but you couldn't afford the fancy seismometer. Is there anything you could do with a whole bunch of nodes to possibly do better than a single node?
We are not sure, as we didn't think about that, but that is definitely one of the results of this finding, that you could use one seismometer or bunch of geophones and see what suits you better.
Thank you for that presentation. So we're gonna bring James and Hussein back up here. In case anyone has kind of big picture questions about field camp, now is your time to ask. Floor is yours.
Questions? Just starting off, thank you all once again for a great field camp and for demonstrating that this is a good use of one's time. I think it's, all these presentations are really good, very impressive, and it was a joy to work with everyone in the field. A question based on the fact that, you did have a very limited amount of time to work with these data. Each group chose a project, you couldn't do everything. I'm curious to hear possibly from individuals whether there were projects that they might have been the second pick project, or having worked through one project, if they had another 2 weeks or a month, they might be glad to work on other projects that could have come out of these data, or I guess conceivably out of data we didn't even collect that folks might wish they had worked on or would be glad to work on if there was an opportunity.
So we got a huge amount of data from deep seismic that wasn't used in any of our projects. I think those data would need more time for processing. So maybe it's gonna be like for future recommendation for senior design maybe, or some other project, so yeah.
Yeah, I would have liked to work, I did a shallow MT and I really enjoyed that, but I also would have liked to work on deep MT or deep seismic and all sorts of things. Like Hussein said, I mean, luckily we can expand on this with senior design or something.
Also, in addition to that, like for the deep MT, for example, we did the inversion for the 81 sites and it's still running from like last week. So if we had like more time, we would have like a bigger grid, a big picture. So we could use more time in processing for any other project.
Any of the other students, is there like a data set that you really wish you worked on?
Or you could still.
Working with the governments, would have been interesting, I think also for our project. Going back and looking at water in the area in more detail would have been really interesting, because any sort of DM methods going to be affected by that. So I think in the future, that might be a great thing to do with students, say, water is going to have an effect on pretty much everything we do. Spend some time, look at that, and figure out what we need to measure so that you can incorporate that to your measurement. We had a very difficult, that was a roadblock for us. We had to, Artie's equation was our eventual solution, but until we got there, we had a lot of spinning wheels about what to do.
We have a question online from Roy. Will the data from this field camp be made publicly available to support future research? If so, where might that data ultimately be stored?
Jack, I'll throw this one to you.
Yeah, let's see, we're compiling all of the data, pre-processed and post-processed currently. It's on a OneDrive that we would be able to share with, any outside, groups. Likely after we end up compiling all of it in the next week or so.
I plan on uploading it to Zenodo as well, so it'll just be publicly available for anyone.
Just two comments there. One, all of the MT data and the broadband seismometer data will also go to the Iris Pascal website as part of the agreement for working with them. And I think that's a great question, sort of relating back to other projects people want to work on. We saw today that one group, TM, went back to previous year's work to add to their research. So 2 or 3 years, someone might come back and look at something. And the MT groups actually looked at data collected from other massive field programs and integrated it. So this sort of open data value, I think, was demonstrated quite well with this year's projects.
Any general question related to field camp, anything?
If not, let's give all these students a round of applause. I mean, 8 days of work to produce this is really incredible.